Section 7.1, Integral as Net Change. Today, ladies and gentlemen, as you watch this video, we're going to be discussing linear motion again. We did that in an earlier chapter. We'll look at a general strategy for solving integral problems. Among those problems, we'll discuss consumption over time, net change, and work. I encourage you to have your calculators ready, as we are going to be using them quite a bit in this lesson. Our first example, the graph below shows the velocity ds dt of a particle moving along the horizontal s-axis for t from 0 to 5, and it asks us to describe the motion. So again, what we have here is a graph of velocity, and from the velocity we show motion. And our equation to represent this graph is given here below. ds dt, which is velocity, is t squared minus 8 over t plus 1 squared. Now the first thing we notice, we do know that v sub 0 or v of 0 is negative 8. We can find that by plugging 0 in down here to the function. And that tells us that at the beginning time the particle is moving left at 8 centimeters per second. From time 0 to around time equals 1.25, which is about right here, the particle continues to move to the left. However, we do see that it is slowing down as it approaches the axis that it's slowing down. At 1.25 seconds, it changes direction, starts moving to the right, and you see that the particle is then speeding up. Example 2, suppose the initial position of the particle in the example we just worked is at 9. What is the particle's position at 1 second and at 5 seconds? Well, to find this, we're going to use integrals. We start with this formula. Now, the 9 that's out front here is the fact that our starting position is 9. And we're going to add to that whatever distance is traveled from 0 to 1 second. Now, why did I use an integral? Well, if this equation here represents velocity, then the antiderivative or integral of velocity would be position. So this gives us the total position change. So starting position of 9, position change from 0 to 1. Now I'm going to just let you type that into your calculators. On the 84s or the CXs both, you should be able to type that in, add 9 to it, and you get a total change of 16/3. Now how's the problem going to change for going to 5 seconds instead of 1? Well, instead of 0 to 1 on the integral, we'll make it 0 to 5. Again, pause the video if you need to. Plug that into your calculator, and you get a total distance traveled of 44. Alright, calculating total distance traveled. Actually, I misspoke on the last slide. I said total distance. It wasn't total distance, it was the final position. There is a difference between final position and total distance traveled. If you imagine a starting point and you think about final position, you could go left and right, left, right, left, right, left, right, and if you ended up back where you started, your final position would be a change of 0. But that doesn't account then for the total position or the total distance that you traveled. So how do we change the problem to make it total distance? Well, this was what we had in order to get a position change from 0 to 5. This is how we make it total distance. Now, by definition, the absolute value of velocity is, of position is distance. So here we're taking the absolute value of our function, and that gives us our distance traveled. Now you plug this into your calculator, and you get a total distance traveled of 42.5869. Now, as we start these word problems with integrals, just want to give you a few tips. You can pause the video now and read over them if you'd like. Probably won't focus too much on number 1. Number 1 to me seems like overkill. It tells us to look at the situation, write a Riemann sum using sigma notation such as you see here, and then step 2 tells you to rewrite it as a definite integral. I don't see any reason to do step 1. I usually just skip on to step 2. And then we'll take that integral and we'll evaluate it numerically or with an antiderivative. So, using that strategy for this first problem, potato consumption. What an exciting problem, consuming potatoes. From 1970 to 1980, the rate of potato consumption in a particular country was C of t equals 2.2 plus 1.1 to the t millions of bushels per year, with t being the year since the beginning of 70. How many bushels were consumed from 1972 to the end of 1973? So we take our integral, we have our consumption formula, 2.2 plus 1.1t. 1972 would be t equals 2. The end of 73 would suggest the start of 74, so we'll use t equals 4 for that one, so 4 right there. And now we, again, simply plug this in. You can work it out by hand if you choose, or on your calculator. It does not matter to me. In the end, it's 7.066 million bushels of potatoes. That's a lot of spuds to eat. Alright, next example. Example 6. Finding gallons pumped from rate data. A pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate the machinery. The rate, which is given in gallons per minute here, you see in the table, in which the pump operates is recorded at 5-minute intervals for 1 hour as shown. How many gallons were pumped during that hour? Now, we can't use a simple integral on this one because we don't have a formula. Now, we could take time, if we chose to enter all this data into our calculator and come up with some sort of a regression, be it exponential, logistic, linear, some kind of a regression, and maybe see if that works. But I'll tell you now that that's not going to work out real well. So since we have numbers and we don't have a formula, the best approach for solving this problem is probably the trapezoidal rule. And hopefully you remember how to do that from a few chapters back. This is what our function is going to look like. Remember, it starts out b minus a, so 60 minus 0 over 2 times the number of intervals. Now, I've got 13 numbers here, but that's 12 intervals. 0 to 5 is an interval, 5 to 10, 10 to 15, 15 to 20, and so on down. So 12 intervals. And then remember, you put the first number for here, the last number goes here, and then all the other numbers have the 2 in the middle. We talked about why that was when we discussed the trapezoidal rule. Now you can punch all that into your calculator, and when you do, 3582.5 gallons of liquid that's been pumped. Alright, the last topic we want to talk about is that of work. When a body moves a distance d along a straight line as a result of some force F, that is what we call work. Work is the force applied times the distance that an object has been moved. Now the thing about the W equals FD is that this is a constant force formula. This only works if a constant force is being applied. When we start putting in varying forces, then we have to change up how we work the problem. Well, we're going to work some of those. The units for work are force times distance. Now, if you're one of those crazy people that like the metric system, we measure that in Newton meters, or sometimes called joules. In the U.S., in the standard system, which we all know is best, we don't use Newton meters or joules, we use foot pounds. Alright, one specific example of work is Hooke's law. Hooke's law applies to springs. Hooke's law tells us that the force required to stretch or compress a string from its natural length is some spring constant k times x, which is the distance that has been the spring has been moved or changed. Again, this k is called the force or spring constant. Every spring has its own constant. Some springs are very loose and easily bendable, like a slinky. Other springs you could pull on all day and probably not get them to stretch out very much. If you've got a garage door opener at home, there's springs that open and pull the doors. Those are not very bendable. Those would have a much different constant than would a slinky. So here's our final problem of the day. Very short lesson today. We like that. It takes 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring from 4 meters? Stretch it 4 meters from its natural length. Now you may be wondering why this is a varying force problem. Well, again, if you have ever stretched a spring or if you compress a spring, you know that the amount of force that it takes initially is very different than the amount of force it takes as you continue to stretch or compress. So the first thing we need to do is we need to find the spring constant K. Well, it tells me it takes 10 newtons to stretch 2 meters beyond the natural length. So we solve for K and we get a spring constant of 5. Now I take that 5 and I plug it back in, and this now is my spring function 5x. I now take an integral. I'm going to start at the natural length 0 and I want to stretch it 4 meters beyond that natural length. And this is my function 5x. Let's work this one out by hand, as it's so simple. That would be 5x squared over 2 from 0 to 4. Plug in your 4, plug in your 0, subtract, and we get 40 Newton meters, or if you chose to, you could say 40 joules. And that is it, ladies and gentlemen. Please make sure you attempt some of the homework. If not, do it tomorrow in class, and make sure you come with lots of questions.